So touching just on copolymers that we introduced on the previous slide. So these are the structures where, say, a linear polymer chain with all of its mers shown here can have two or more monomers included. So we saw that a moment ago with polyethylene and polypropylene isotactic. So a random version, as we indicated, would be random inclusion of one mer in the chain of the other. An alternating copolymer would be a perfect pattern between one mer and the next down the chain. And a block copolymer, we would position large segments of one mer type together and then transition to another mer type for the next appreciable length of the chain, and perhaps repeat that several times. And we mentioned a graft copolymer where we add one polymer chain to the main chain via a graft site, where the one main chain hosts other polymers that are foreign, if you want, to them. Okay. Touching on the idea of SBS, SBS is a common material, or even ABS is a common material for thermoplastics for bumpers on automobiles, for example. So here's the case of SBS. We see that there is a styrene, a butadiene, styrene copolymer, and it is a block copolymer. So recalling we're in this configuration here. Looks like there are two different types of mers, styrene and butadiene, and the styrene is all together. Then there's a butadiene segment and then a styrene segment, and that finishes off the pattern. So this component of the diagram doesn't exist. We see those ideas reflected in this more precise diagram here, where styrene segments are indicated as blue and the butadiene segments are indicated as the red. What we know about butadiene is that it is a very soft material. It is very low thermal transition properties, so it adopts more of a amorphous, near liquid, high viscosity state at room temperature. But the styrene component is a high thermal transition property material because of the complex side chain that is this benzene. It makes it difficult to have styrene blue chains move past each other given the bulk of this benzene group, kind of like an anchor hanging off of a boat. That anchor is difficult to allow the rest of the boat to travel, so the styrene chains make it difficult to allow blue chains to move. What's also known about copolymers is that they do not like to mix. So in a sense, they phase separate just like oil and water in your vinaigrette. So butadiene segments like to mix with butadiene segments. So that is, for example, red to red segments like to happen, and red touching blue segments does not like to happen. So the styrene segments want to come together, and we'll get separate domains of these that are all styrene in composition, where those blocks from neighboring chains come together and give us a phase or a little puddle of polystyrene with many chains contributing to that. The styrene, as you can see here, is the hard component. It's high glass transition temperature, high temperature to flow this material, and the butadiene is soft. So here we have the combination of a hard, soft set of polymers, and we get a nice combination of properties as a result of that. Notice the diagram also shows that there's no crystallization, so the material is fully amorphous as a result of the complexity of the chain being a block copolymer, as well as the sort of temperature conditions and the selected materials. Before we leave that topic, so it turns out that in order to flow this material, the glass transition temperature, the temperature at which those blue chains can start to snake and move past one another, glass transition, so TG, this is on the order of 100 degrees C, and the butadiene segment is below room temperature, glass transition temperature. So to reprocess this material, you would have to heat it above 100 degrees C if you wanted to reform it into a new shape. The elastomeric property of the material comes from the fact that this butadiene segment is very high viscosity fluid-like, so it can absorb energy on impact, put all that kinetic energy from the striking object into molecular motions in the main chain. The high glass transition temperature of this SBS elastomer acts as the physical stitches to keep all materials anchored together so that the material can have its permanent form at the temperature condition of room temperature. Of course, above 100 degrees centigrade, it will flow and allow us to reuse this. So this is the sort of success of the SBS elastomer, is that it's a nice, robust, rubber-like material that can be reprocessed. Okay, what other additives can be used with polymers? So we might add materials to improve mechanical properties, processing, or durability. For example, fillers can be added. So these might improve the tensile strength. So that is the highest stress point on our stress strain curve. They might add abrasion resistance, toughness, the area under the stress strain curve, perhaps even decrease cost if the polymer is expensive and the filler is cheaper. Some common materials to consider there are carbon black, silica, which is cousin material to sand, so quite inexpensive, wood flour, glass, limestone, even talc can be used there as fillers. Plasticizers can be used to help with processing and other temperature transition adjustments. So for example, they can be used to drop the overall glass transition of the material by providing more molecular free room or space, because the added plasticizers will help to extend neighboring chains away from one another in a sense. So that extra volume provided between chains allows the chains to snake past one another at a reduced temperature. So this allows otherwise brittle polymers to be a little bit more ductile in the presence of a plasticizer. So where is this common? These are commonly added to PVC, given that the secondary bonding is so strong. And so to suppress that a little bit, plasticizers can often be used there to manage the brittleness of polyvinyl chloride. Okay, stabilizers. So like many of you have maybe experienced with your plastic lawn furniture or patio furniture, they can discolor or fade in the sun. So if we can protect against oxidation with antioxidants or UV protectants, we can install those into the plastic to prolong the lifetime of the thermoplastic out in the environment where direct UV exposure might exist. Even lubricants can be added. So this would be a processing material to help polymers slide through processing equipment a little easier. So things like salts of long fatty acid molecules, like the salt of a soap, sodium stearate, can be used to help the material slide through the machinery and dyes, as we'll see in a moment, a little easier. Of course, colorants and dyes to make the final thermoplastic material desirable for its ultimate service use. And even flame retardants is a big industrial area, especially in the aerospace industry, where having self-extinguishing thermoplastics and thermosets is vital to passenger safety.